This is Lisa Schaefer, and I will be kicking off Module 2 of our 4-part series. And I think you'll find today's session rather informative. I want to remind you that we are recording, and so we do ask that unless you're asking a question, that you please keep your microphone muted. We will have plenty of breaks between the modules because these are a little bit longer, and we will have a quiz followed by a quiz review towards the end of the module. And this is a reminder that although the quiz doesn't count for course credits, the review of the course is informative and is considered instructional. So therefore it is included in the total number of credits or PDHs that we calculate. So with that, I should probably bring up the agenda for today. If you haven't already downloaded the handouts, they're in the chat. And this is the module that you see, the agenda that you see on the screen for the module. So once again, credits are based on 50 minutes of instruction for every hour of the course. So I think we should hit our 3 PDH or 0.3 CEU target for today. Okay, so now most of you know, I think someone else has their microphone on, so it's causing an echo. All right, most of you know that the stormwater rules specify the methods that may be used to calculate stormwater runoff, and that's what I'll be covering during this first part of the module. And for those of you who are wondering why this material is included, well, we mentioned in Module 1 that the DEP conducts audits to assess how well its permittees are following the requirements of the permit, and part of that includes stormwater calculations. Now, I know that most people are familiar with the methods, but based on what we've seen in the audits, the calculations themselves are not always performed correctly, and then that generally can mean that the reviewers themselves have not caught these errors. So we will focus a lot on that, and you will actually see in later presentations in modules 3 and 4 some of these errors. So all right, so we introduced the basics in module 1, and that brings us to this presentation. So we will cover the methods allowed under the Stormwater Management Rules, how to use the Natural Resources Conservation Service, or NRCS methodology that was formerly often referred to as TR55, to calculate everything, peak flow, volume, and produce hydrographs. The NRCS method was previously also known as the Soil Conservation Service, or SCS method. So you may still see these two acronyms used interchangeably. Our third goal today will be to calculate the time of concentration, and we'll cover some of the examples in the revised version of Chapter 5. And after that, we're going to talk about when exfiltration may be used in stormwater routings, which is new. And the last goal is instructing you on the correct way to use the rational method when sizing a manufactured treatment device with this methodology, particularly when you're using flow rates as the design criteria. Sorry, something is wrong with my slide. To comply with the rules, stormwater calculations are required for rainfall or for storm events that are associated with groundwater recharge, stormwater runoff quality, and stormwater runoff quantity, and the rules are very specific as to the methods that may be used. The requirement is found in the amended rules at the location that you see printed in the green subtitle. So we'll start with the item that is number 2 on the list. And the two methods that are shown on this page have limitations as to what they can calculate. So that's why the two are often used in conjunction with each other. The rational method is used for determining peak flow rates, and the modified rational method is used for hydrograph computations. Now, the rational method, it's been around since 1889 or so, and it's used to estimate peak flows for a specific rainfall intensity, but it cannot provide total stormwater runoff volumes, nor can it be used to produce hydrographs, and for that we use the modified rational method. Now, for more information on these, you may refer to Appendix A-9 in the New Jersey Soil Erosion and Sediment Control Standards, and that is available at this link. Now, I will talk more about the rational method towards the end of the presentation, and that is because although after we published our revised Chapter 5, we had received a lot of comments requesting that we eliminate it, but it's still in the rules, so it's allowed for the time being. So for the modified rational method, this information is best covered in Chapter 5, and I'll leave that to you to read on your own. So that takes us back to the first method of the rule citation. That is the USDA Natural Resources Conservation Service, or NRCS methodology, which was additionally described in TR 55. However, TR 55 has been superseded by the National Engineering Handbook, or NEH, in Part 630, known as Hydrology, for which I provided the link that is currently in use. The NRCS method can provide total stormwater runoff volume, the peak flow rate, and it produces hydrographs. Under the NRCS method, different synthetic rainfall distributions and unit hydrographs can be applied to produce the stormwater runoff hydrographs in accordance with the geographical differences that may affect rainfall patterns in each storm event and the runoff pattern in a region, and that could be dependent on whether the slope is steep or flat. Now, there's plenty of software packages out there that use this methodology, and in later presentations, you'll learn what to check in your reviews. The NRCS method can be used for a drainage area of any size, but the area is still subject to the rules requirement that the relative stormwater runoff rates and/or volumes of pervious and impervious surfaces be separately considered to accurately compute the rates and volume of stormwater runoff from the drainage area. Sometimes it's called the curve number method. And in the NRCS methodology, the runoff equation, or CN runoff equation, was developed to estimate total storm runoff from the total storm rainfall. The soil and cover conditions determine a unique parameter called the curve number, and that's what I'll be covering for the next few slides. So by using the NRCS equation, we calculate the runoff depth represented by the parameter Q in inches. P is our rainfall data for a particular design storm. Initial abstraction is all of the losses before runoff begins. It includes water retained, surface depressions, water intercepted by vegetation, evaporation, and infiltration. For New Jersey, initial abstraction is equal to 2/10 the potential maximum retention represented by the parameter S. After determining the curve number and calculating the value for S, values are inserted into this equation and we calculate the total depth of runoff. So CN is an empirical parameter used for predicting direct runoff or infiltration from rainfall excess. It's a function of the hydrologic soils group, which we abbreviate as HSG, and land cover such as woods, pasture, agricultural use, percent impervious, and so forth. A is the most permeable HSG and produces the least amount of runoff when thoroughly saturated. The designations then go alphabetically from B to D, with D being the least permeable and having the highest runoff potential. The preliminary soil group classifications are found on the NRCS Web Soil Survey, but further investigation is typically necessary. And Changyi will cover that in our next presentation, which is on soil testing. He will also cover the default values one may assume under certain conditions. So once you've determined your HSG or are using the defaults that are allowed, you can determine the curve number value to input. So as I said, they differ as a function of land cover and soil group. So shown on the right table is table N-5 from the NEH. And there are a lot of different land uses, but you'll mainly see those here by the double arrow. Notice that CN increases as the soil group goes from A to D. And what does that mean? It just means that there's going to be more runoff for a D soil than for an A soil for a particular land cover description. And it's crucial to use the CN value that best mimics the ground cover type and hydrologic condition. If the analysis uses pre-development CN values that are lower in value, the analysis is considered to be conservative. If the analysis uses CNs that are too high, the analysis is incorrect. So note the requirement from the stormwater rule shown in the yellow shaded box at the upper left of the slide regarding which CN values to use. Presume that the pre-construction condition of a site or portion thereof is a wooded land use with good hydrologic condition. The double arrow indicates the particular row where these values are in table 9-5, and this requirement often typically appears in the SCO, or should appear in the SCO. But do remember that for an impervious surface, the curve number is always 98. Lastly, I want you to note the cautionary information in the white box on the left-hand bottom corner of the slide. That means the values in the red box on the table are not what you will typically see in your calculation for a development project. So due to the nonlinearity of the equations and losses from initial abstraction, it's important and also required in the rules to compute separately the runoff volumes from the pervious and impervious areas instead of averaging the curve numbers. Particularly for your smaller or more frequent storms, averaging undercalculates the volume of runoff generated by the impervious surface on a site that also has pervious land cover if a composite CN is used to compute the rates and volumes of stormwater runoff from the site. Using composite CN values is a common error that we see in our audit reviews. So for example, if we analyze a site with 1 acre of impervious with a curve number of 98 and 2 acres of grass lawn with a curve number of 65 for the water quality design storm, using a composite CN for the site would result in roughly 70% less volume than if the volumes were calculated separately for pervious and impervious areas. So using a composite CN means the BMP is likely undersized for the smaller storms, particularly water quality. And when that happens, the BMP does not merit the pre-approved rating for the total suspended solids removal. So here's a better proof from Chapter 5. So a portion of a major development consists of a 200-foot wide, 25-foot long impervious surface and a 200-foot wide, 75-foot long grass lawn area that are separated by a grass swale. The soil is identified as HSGA. The 2-year design storm produces 3.5 inches of rain over 24 hours. The slopes of the impervious surface and the grass lawn are each 1%. So in other words, the runoff from the impervious surface will flow directly into the grass swale. And of course, I looked up the CN for grass from table 9-5 and it is 39. And of course, the CN for impervious is always 98. So here we'll calculate the volumes produced for this storm using the correct method and the incorrect averaging method. Using the Nrcs runoff equation, we calculate S, our potential maximum retention, using our CN values and input the rainfall data to calculate the depth of runoff, which we then multiply by the area on which it falls to compute the volumes. In this example, look at the yellow shaded box. Averaging the CNs yields a volume that is only 37% of the total volume we calculate when following the rule requirement to compute runoff separately, as shown in the green box on the left. Now, I do want to move on to the next section, but you are free to enter questions on this subject using the chat option, and we'll take a short look at those questions and any for the next topic in just a few slides. Okay, so with that, we're going to move on to goal 3, calculate time of concentration. So previously we saw the definition from the rules that it is the time required for stormwater runoff to travel from the most hydraulically distant point on a site to a point of analysis. T sub C, or TC, is an important parameter to get right in our calculations. So let's look at the next graphic to better understand why. So a site consists of one or more drainage areas, and a drainage area is basically a land area where all the runoff produced by the area converges to a single point. Sometimes we call these drainage basins, and they're determined by the topography, and they can range in size up to millions of square miles. So by looking at this watershed, you'll see that due to the slopes of the areas, any drop of water that falls in the valley between the two shaded bars, left and right, eventually makes its way to the river and then down to our point of analysis. Any drop of water that falls on the other side of the ridgeline will flow away to somewhere else. So we're not going to worry about that. But we have to remember that the most hydraulically distant point doesn't necessarily mean the furthest point in distance. So in this image, the surrounding terrain on each side up to the ridgelines are part of the drainage area directing runoff to our point of analysis at the red dot. So even though runoff may have to move further to get from the mountains up here, the most hydraulically distant point may be in the forest because of leaf litter and varying slopes and so forth. So in Module 1, we learned that various land uses, slopes, and other factors all affect how fast stormwater actually moves across the land. So dense vegetation, like forest, causes runoff to move more slowly than smoother land surfaces, and certainly steeper slopes cause runoff to move faster as well. To compute the time of concentration, surface roughness, channel shape, and slope are the three parameters that must be characterized for each segment of flow along a flow path. Additionally, the energy level of the flow also factors into the calculation. The three types of energy are sheet flow, shallow concentrated flow, and channel flow. Now, the first two are more likely to occur, but in case you don't know what I mean by sheet flow, it's usually at the headwaters and over plain surfaces. And this is where runoff forms a thin film that is low in energy, velocity, and depth. And this is what you might see on lawns or in parking lots when rainfall begins. And in Chapter 5, sheet flow does not occur after 100 feet. And there's more to cover on this in a slide or two. Now, shallow concentrated flow occurs where runoff begins to coalesce and picks up velocity. The depth is more than 1/10 of a foot, but it still has no defined channel. And channel flow can be seen in your aerial photographs and on GIS, of course, and it would be represented on the USGS maps as blue line streams or with dashed lines where there's piped flow. And it's essentially flow in some type of bounded channel, which is higher in energy state and relatively faster than the other two types. So now that we understand the types of flow energy, let's put them to use. So from the NEH, the velocity method is used for a project site or drainage area, and the time of concentration is the sum of all of the travel times T sub T for each type of flow in a segment among the most along the most hydraulically distant flow path. You can have more than one occurrence of sheet flow, for example, because one of the defining parameters such as slope has changed. And this requires a calculation for each type and instance of flow over the segment or path, and then we simply add them all up. So going forward, the assumed minimum value of 6 minutes that was previously published in Chapter 5 must now be replaced by a correct calculation. Therefore, it's important to check the reported values in your reviews. If TC is calculated incorrectly, it could potentially impact the neighboring land, the infrastructure, or even a local waterway. Revised Chapter 5 also changes the maximum sheet flow length in accordance with NEH Chapter 15. For the pre-construction condition, assume sheet flow occurs for up to a maximum of 100 feet, unless there's something physically in contact with the flow of stormwater runoff, such as a swale, a curb, or inlet, to prevent sheet flow from occurring. That is, by increasing the depth of flow in excess of 1/10 of a foot, regardless of whether the surface is impervious or pervious. If the site conditions only create 75 feet of sheet flow, use 75, but the maximum value that you can use is 100 feet. For the post-construction condition, the maximum distance for which flow occurs as sheet flow is 100 feet, and the distance over which it occurs, L, must be calculated using the McEwen-Spies limitation. Remember, if the sheet flow length calculated by the McHugh and Spies limitation criteria exceeds 100 feet, you must limit it to 100 feet. Now, I haven't covered these variables yet, so let's do a little bit more before we get to an example. So let's look at the equation for sheet flow, and these are the parameters that must be identified. The Nrcs methodology uses Manning's kinematic equation for computing the travel time T sub T of this segment. There are the variables. These are the variables that we will need. The roughness coefficient, Manning's N, is found in Chapter 15 of the NEH. Obviously, it's a measure of the roughness of a surface, or you can think of it as a measure of the resistance to flow. And there are different tables for each energy state of flow. So it's important to make sure you're using the correct table. So for sheet flow, these are arranged from smooth to rough. You must verify the correct surface description is used. So for dense grasses, we would use 0.24 in the calculation for the travel time for sheet flow. Now, the lower the N value, the quicker the runoff will travel, and that's why impervious surfaces have a roughness coefficient of 0.011. And the BMP manual states that the maximum roughness coefficient for sheet flow in New Jersey is 0.40, and that corresponds to woods with light underbrush. And in a little bit, we'll calculate T sub T for sheet flow in an example. So we need our 2-year 24-hour rainfall depth to compute the value. And this is just a partial screenshot of the NOAA precipitation frequency data server data. And we got here by selecting precipitation depth and partial duration for the time series type. And you will wind up with a chart that's much larger than the piece that you see here. But basically, you find your 2-year storm in the columns, and then you find your row for the 24-hour duration, and the rainfall depth that is listed is 24 inches. So for this chart, our rainfall depth that we need is 3.3 inches, and it's circled in red, and coincidentally, this is for Trenton. So of course, you could also use the county data that was introduced in Module 1 for this storm. I'm going to stick going forward with this data source. So let's see how the travel time for shallow concentrated flow is calculated. Basically, travel time is equal to the length, excluding the initial sheet flow, which is less than or equal to 100 feet, divided by the estimated velocity. We multiply by 3,600 for the conversion from seconds to hours. Now, velocity is estimated based on the site's surface condition and slope. And for that, we determine that from figure 15-4 in part 630 of the NEH. The velocities plotted are average values, and they're a function of the watercourse slope and the cover condition of the channel. And this source was derived by solving Manning's equation for a wider variety of different land covers. The y-axis is our slope in feet per foot. The x-axis is the average velocity in feet per second. You find your slope, you draw a horizontal line from the y-axis over to your cover condition, and then draw a vertical line down to the x-axis to find the value for velocity in feet per second. Now, you may still see citations for a source that came from TR 55, but you must remember that that has been superseded. So you must make sure that the graphical source, if one is used, is this one. So the last travel time we need to calculate is for open channel flow. And for this calculation, we need the open length of the segment, which is the roughness coefficient for open channel flow. And that's different from other N values previously covered. We also need hydraulic radius and, of course, the slope. Manning's N values for open channel flow can be obtained from standard hydraulics textbooks. Hydraulic radius is equal to the cross-sectional flow area divided by the wetted perimeter. That is, the surface of the channel bottom and sides that are in direct contact with the water. Now, don't use this equation for flow under pressure in a pipe. You shouldn't see that too often in your stormwater calcs. Okay, so we have our 3 different types of segments. So let's go through an example for calculating time of concentration. So for our post-construction condition, stormwater runoff flows through a wooded drainage area along a flow path measuring 100 feet in length, consisting of sheet flow over an area with 0.5% slope and shallow concentrated flow over an area with 1% slope. So a slope of 0.5% is 0.005 feet per foot, and for woods, Manning's roughness coefficient for sheet flow in New Jersey is 0.4. The sheet flow length is calculated using the formula from the McEwen-Spies limitation criterion, as this is the post-construction condition. And we previously obtained our 2-year rainfall depth. So we plug all this into the equation. We get L is equal to 17.68 feet, and we get a travel time of 9.18 minutes. So remember, the total flow path length is 1,000 feet. So sheet flow was 17.68. So therefore, the length of the shallow concentrated flow segment must be the remainder of 982.32 feet. The value for the flow velocity is determined from figure 15-4, as I showed earlier. And so for this example, we project a horizontal line over from the y-axis at the tick mark, denoting the 1% slope, to the curve representing the forested area. And we get a corresponding velocity of 0.25 feet per second. We then enter that into our equation, and we get a travel time of 65.5 minutes. Are we done? No, we need our answer. We just sum up the travel times for all of the segments along the flow path, and our time of concentration is 74.7 minutes. Okay, so let's take a look at the questions, and I can turn on my chat now so that I can see them. Mr. Moderator?
Yep, so it looks like we got a couple questions here. So first one seems like more of a clarification. Is the maximum sheet flow 100 feet or 150 feet?
So with the revision to Chapter 5, it is now revised to 100 feet. You have to look at for the precondition, there are slides on that. For the post-construction condition, you use the McEwen-Spies limitation criterion. Those are was part of all of Chapter 5 that was rewritten.
Then the other question is it proper to request designers to show step-by-step calculations on the stormwater calculations?
You may see some simplified calculations, or you may have to make a guess. I generally check a drainage area map to make sure. I often see them on there as a text box that's been superimposed, or you can do a quick calc to see if it makes sense. So you may have to scale off hopefully they've provided the drainage area map, if not a grading and drainage plan, or even the soil erosion plan, to see what flow path you would use, and then see if that's one that they used. Chengi, did you want to weigh on that?
Okay, I think the question regarding whether design it's proper to request designer to show step-by-step calculation on stormwater calculations. I think that would be if the stormwater measurement report submitted to you shows unclear or not enough information for you to determine whether the calculation has been done right. I think you can ask them to clarify and have more steps to show that how they reach to the conclusion of the results that in the report.
Oh, additionally, the model's SCO does have language in it as a sample of what can be required as part of a submission. So a municipality can request more by codifying it into their ordinance. Okay. Tony, you had asked if TC is 2 minutes, do we use the minimum? You're going to use the calculation. So that the minimum is replaced always by calculation. Chengi, do you want to clarify that?
Yes, if the calculated T sub C is 2 minutes, then you use 2 minutes. For the Nrcs method, there's no minimum T sub C in the new Chapter 5.
That appears to be it for questions in the chat.
Okay, so that is great. So then, Mr. Denning, I saw your question, and I'll look into that, and I will have to get back to you. And but I always go by the most hydraulically distant, so I tend to do a number of calculations. Oh, we have another question, Changi, that I would ask that you would look at.
The question is because the new rule focus a lot on small drainage areas for T-sub time of concentration times. Can we reasonably accept a minimum T sub C equal to the model's analysis step time? I don't know what you mean that the model's analysis step time. If I know some software has the minimum time step for the software to run the calculation, but my experience that, for example, you can still use 2 minutes as the T sub C in the software when you do the modeling. So I don't quite understand the question regarding what the model's analysis step time. Okay, yeah, the step time says that increment time for analysis. As I said that some model that has a minimum like 5 minutes or 1 minute for the analysis time. I think if the model that has the calculation limitation, even you put the 2 minutes and it's shorter than their analysis time, the software might just use their default value. I don't know how much is that, but technically, if you calculate the T sub C is 2 minutes, then you have to use 2 minutes to carry over the calculation. And the other question that does the RSIS still consider the RSIS, the residential site improvement standard, still consider minimum time of concentration for residential development as 10 minutes. We don't know. We have to check that whether RSIS in the rules they have that still require that that information and get back to you.
Okay. One more question and then we're going to move on. And it says, I believe HydroCAD needs to be updated to comply with the new rules. Have they been contacted?
As I know, HydroCAD has some new build numbers that has been matching our new chapter 5. For example, the NOAA C and D rainfall distribution is already in the HydroCAD model. And for the calculation of the shear flow path, I haven't seen HydroCAD have the function to calculate the length of the shear flow. So you may have to calculate that in offline. Then you input the length of shear flow into the HydroCAD model.
All right, I'm going to move on to the next subsection. Okay, so the next thing that we have to talk about are hydrographs, the graphs depicting the flow rate of runoff versus the time passed at a specific point of analysis. A hydrograph provides much information about stormwater runoff, including our time of concentration, when peak flow occurs, peak flow rate, and the volume of runoff generated. So first off, this is never anyone's favorite part, but we have to talk about the unitless and synthetic hydrographs for the Nrcs methodology. So a unit hydrograph is a direct runoff hydrograph resulting from 1 inch of excess rainfall. The unit hydrograph influences the shape of the runoff hydrograph, particularly the peak rate of discharge. So given a watershed's unit hydrograph, one can calculate the theoretical hydrograph for any storm event. And in an ideal world, a unit hydrograph would be developed by metering the flow off of a watershed. But since we can't meter everything, we use synthetic hydrographs instead. And 2 synthetic hydrographs were developed for determining runoff hydrographs for our unmeasured watersheds. The 2 that we generally use are the Soil Conservation Service Dimensionless Unit Hydrograph, the SCS, and the Delmarva Dimensionless Unit Hydrograph. And most software packages that are out there now have the settings that allow for selecting either one of these. So first, let's talk about the SCS. And that's based on an average of natural watersheds with various sizes and geographic locations, and that allows us to predict how an unmetered watershed will react to rainfall. So first off, we need to note that the SCS unit hydrograph can be used anywhere in the state of New Jersey, and shown here with an orange curve is the SCS unit hydrograph. The corresponding rainfall event is shaded in the upper left-hand corner in the turquoise box. As you can see, the timing of the hydrograph, it's based on the time of concentration on a site, and I've highlighted that T sub C with yellow. There's some runoff at the start of the event, and then more and more areas up gradient of our point of analysis start to contribute. After the time of concentration, the farthest away areas stop contributing, and runoff continues to taper off. The volume of runoff produced by the site in response to our rain event is equal to the area underneath this curve, right, the hydrograph. So runoff discharge is non-linear in relation to the time of the rain event in accordance with our NRCS observations for many natural unit hydrographs that were developed over many various watersheds. The dimensionless unit hydrograph has a peak rate factor of 484, and that means that 48.4% of the total runoff volume is discharged before the peak time, and that area is shaded in light purple. 51.6% of the total runoff volume is discharged after the peak, and the peak rate of runoff is the maximum height of our hydrograph. Here, okay, so you can see that the shape factor usually appears on your printouts, and that's definitely something that you want to check in your reviews. And I bring this up because we also have the Delmarva unit hydrograph, and that's suited for the flat coastal areas of Delaware, Maryland, and Virginia, which is where it got its name, and also those same areas in New Jersey. But outside of flat coastal areas, Delmarva cannot be used. So when you calculate the peak flow using the Delmarva unit hydrograph, we use a constant shape factor that's lower than that for the SCS unit hydrograph. And if we broke down each individual equation and developed it, we would see a shape factor of 284 or 285. I've seen both depending on the software package that's being used. Well, wait, what does that mean? The lower peaking or shape factor for the Delmarva means that there's less volume under the rising limb here, the left side of the peak. Okay, in other words, the hydrograph is shorter, but it's also longer in duration. So that comes in part from the gentler slopes of the terrain, the lower level of urbanization, and so forth that led to this development. All right, so let's move on. I've added this slide so that the current information from the department is all in one place. The NRCS, in the supplement attached to the New Jersey Bulletin from September of 2003, stated that the use of the Delmarva unit hydrograph may be used in watersheds in the coastal plain region of New Jersey that are characterized by flat topography, meaning average watershed slope less than or equal to 5%, low relief and with significant surface storage in swales and depressions. The scope of usage was restricted at that time to conditions without urbanized area due to limited experience using this unit hydrograph. However, a 2018 bulletin updated the usage and rescinded some of those limitations. So, use of the Delmarva unit hydrograph will not affect the determination of runoff volume, but should result in lower peak discharges when compared to the standard unit hydrograph. So you can only use the Delmarva in the coastal plain. However, you can opt to use the standard unit hydrograph there as well. But regardless, the same type of dimensionless unit hydrograph must be used for both pre and post-development hydrographs. So projects that lie on or near the boundary between the Piedmont and the coastal plain should be modeled with both the standard and the Delmarva unit hydrographs and the results compared with actual field conditions to determine which offers a best fit. So wait a minute, what do I mean about near the boundary? So I just zoomed in on this image and I added a few points of interest. So the blue line dividing the Piedmont from the coastal plain is the boundary. It's not a stream. The hyperlink in the header is the Bureau of GIS systems that will give you some more information. And the other link below the image is to get shapefile data for our GIS users. So you'll want to be careful in outlying portions of locations that are near this boundary. So that might be portions of Princeton and Monmouth Junction, maybe if you're a little northwest of Trenton or just south of Carteret, just to name a few. And the lower GIS link is probably your best bet for those situations. And alternatively, your municipal stormwater management plan may include information as well. All right. So later on in our how to review a project presentation, you're going to learn more about when the Delmarva unit hydrograph should not be used. Okay. In addition to the rainfall depth data, we have to know how rain falls during a storm event if we're going to create models and design our BMPs to address runoff. To achieve the goal of estimating a rainfall event for design and planning purposes, between 1961 and 1977, NRCS developed synthetic rainfall distributions from historical records for different regions of the country. And the basic shape of those distributions assumed that rain started gently, it increased in intensity, and then tapered off. And the type 3 distribution was previously used for almost 20 years. However, now we must all use NOAA C and D distributions, depending on which county we're in, per the 2012 bulletin from NRCS. And I will say that a coworker has been doing modeling with these, and we've learned that you can expect to see higher peak flows when using the C and D rainfall distributions. So this is just a map depicting those regions, and you should be able to download text data using this link. And additionally, under the Chapter 5 on the BMP webpage, we've added a link to make this information available as an Excel file for your use as well. So at this point, I will ask if there are questions, and it looks like there may be. I can't back up. Let me see.
Yes, so there are a couple questions here.
Okay.
So let's see. So one of the questions is, well, I think Cheng-Yi might have gone over that already, but he was referring to Mike's question about informing HydroCAD, and he said he'll inform them. We have another comment here, above clip from RSIS NJC 5:21-7.2, and it reads, in all instances, design engineers shall use a minimum time of concentration of 10 minutes. That is for storm sewer design, a 10-year to 25-year storm frequency. So that was something that was pasted in the chat.
Is that the year can't be right on that one citation? May 3rd.
Yeah, my word in that the question the question regarding the RSIS standards that have 10 minutes minimum time of concentration. That section under RSIS chapter 7.2 that is applicable is the starting of the that citation says that when using the rational method and then have following some about the how to use it, and one of that is that the minimum time of concentration is 10 minutes. So I believe that means the rational method that in according to RSIS, you can use 10 minutes as the minimum time of concentration. But these are just what these are presented for the time of concentration is that under the Nrcs method.
Right,
So,
I will be doing
yeah.
rational method towards the end of this presentation.
Yes, so, yeah, so we just want to clarify that.
Thanks,
Another
Jim.
question here is one of the common mistakes designers make is using the Delmarva hydrograph. They're asking, would Chapter 5 correct this wrong assumption?
So I'm not quite sure. So you can use Delmarva in the coastal plain, unless you're near the boundary and you have to figure out which is the best fit. But if you're going to use Delmarva, you use it for both pre and post. But you can't use Delmarva in the northern parts of the state.
Another question here. So would no minimum TC apply just to projects not under the jurisdiction of NJAC 5:21?
Changi, do you want to field that one?
I think the I have to check that other than the citation I just mentioned regarding use of the rational method, I have to check the RSI standard whether it says about the time of concentration for using Nrcs method. I believe that they and the RSI standard points most of its content to our 7 column A, section 5 and 6. So if there is nothing addressing the minimum time of concentration for Nrcs method, specific spell out in the RSI standards, I think that would be referred to our stormwater management rules.
And we have one last question. I realize we're probably going to run over, so I'm going to move this along. You indicated that the SCS may be used in place of Delmarva. Yes, the SCS can be used anywhere in the state. It's the Delmarva that has a restriction to use only in the coastal plain. So the SCS has a higher, remember, has 48.4% under the rising limb, whereas, what is it, 28.4, 28.5 is only under the rising limb for the Delmarva. And so its tail end is longer. So that so they're really, so you can use either one in the coastal plain, but you can only use SCS outside of the coastal plain. Does that answer your question? I can't say.
Said no.
Oh, okay. I'm not seeing all of the questions. Uh-oh. All right, so let me see.
You want me to read it to you, Lisa?
No, I just got my scroll to work. Okay.
Okay.
What? All right, I'm gonna have to reread chapter 5 then, and because
I think that the question regarding that what is to prove the the condition within the coastal plain are not suitable for Delmarva use. In Chapter 5, we do have that citation to the Nrcs. It's that the average watershed slope less than 5% and have low topography relief that significant surface storage and have other conditions. So if that the engineer for redevelopment projects, the area has been graded more steeper and has a lot of impervious surface, and at that such condition, then you may use SCS method for the pre and for the post.
Yeah, some of the limitations that were in the original bulletin were rescinded. So I don't have in front of me the 2018 bulletin that updated the usage. So I will have to stick a pin in that and get back to you on that. All right. So where were we? We were on there. Okay. So I'm going to move on because we are running a little over for this presentation, but we will have time later in the day for more questions, and I will try and research more while the next presentation is underway. All right, so let's move on to unconnected impervious cover. So an important approach to managing stormwater runoff is new impervious cover that's not directly connected to a site's drainage system. And this is certainly more important now with the GI requirements under the rule amendments. So to slow down runoff generated by impervious surfaces, certain key aspects must be addressed. Runoff from unconnected impervious areas must undergo sheet flow onto adjacent pervious areas where a portion of the impervious area runoff is given an opportunity to infiltrate into the soil without causing erosion and further sediment transport to whatever's down gradient. Under certain conditions, this technique can help provide both groundwater recharge and stormwater quality treatment for small rainfall events, as well as reduce the overall runoff volume that must be treated and or controlled in the down gradient BMP. So there's 5 conditions that must be met for an impervious area to be considered as an unconnected impervious surface. These are the first 2, and basically the runoff must enter the pervious area as sheet flow, and it must remain that way. The other 3 conditions ensure stability and maintain the sheet flow. For this reason, there is a limit on the steepness of the slope in the down gradient pervious area. The maximum slope of the down gradient pervious area is 8%. All right, there are 2 methods that may be used, and there are 3 requirements applicable to either method. Okay, the area beyond the maximum sheet flow path length cannot be considered in the calculation. All right, the maximum sheet flow path length across the unconnected impervious surface is 100 feet, and we must have a minimum sheet flow length across the down gradient pervious surface of 25 feet in order to maintain that state of flow. The 2 methods that we can use are the Nrcs composite CN with unconnected impervious. That's in Chapter 9 in the NEH, but that has a limit on the areal ratio of impervious to receiving pervious surfaces. And the other method is the New Jersey 2-step method, and that's what I'm going to cover. So in this case, for our example, we've got sheet flow that doesn't exceed the maximum flow path length over the impervious area. And let's see, it also meets the minimum distance of travel as sheet flow over the down gradient pervious area as well. We use the NRCS runoff equation from earlier to compute the volume generated by the pervious area, and our answer is 1,362.5 cubic feet. And the next step is to assume that this runoff is evenly distributed as rain falling on the adjacent pervious surface, and we make sure that the maximum flow path on the pervious area is less than or equal to 100 feet, and that's not an issue here because we've got 75 feet. So, to convert our runoff volume produced by our 2-year design storm, that's the runoff volume on the impervious area, we divide the volume that we previously calculated, we convert our units, and we add it to the 2-year rainfall to get the total effective rainfall. We call that variable the clunky long name of P sub 2I plus P, and that value is equal to 4.59 inches. Okay, using the NRCS equation for the pervious area, with this total effective rainfall, we get the effective depth of rain falling on the pervious area. We finally then convert that depth to volume by multiplying by the pervious area, and we get our answer. So that's a good size reduction in volume. All right. So are there any questions on unconnected impervious? If not, I'm going to move along. This is in chapter 5, if you need more examples. Okay, so the other recent updates to chapter 5, I'm going to review the information, but it's covered in more depth in chapter 5. So you can use exfiltration in routing conditions under certain conditions, and you're going to refer to pages 7 and 8 of chapter 5. Exfiltration is only allowed for certain small-scale GI BMPs that infiltrate runoff. The conditions include soil testing must follow chapter 12, which we'll cover in the next presentation. You must follow all the design criteria that is in the respective chapter for that BMP. And pretreatment must be included unless otherwise so stated in the BMP manual, except for those really small scale BMPs whose drainage areas are less than or equal to an acre. So we're going to take a little detour and look at pretreatment for a slide or two. So by now you know that we revised the BMP manual. Chapter 9 is the BMPs that are small in scale, and they're green infrastructure because they allow stormwater to be treated through vegetation or soil, or provide for reuse, or they infiltrate runoff into the soil. The other BMPs, we've got chapter 10, and they can be GI under certain circumstances or certain conditions, but their use of their limitation is detailed in the summary on their cover page. And then they're also listed in table 5-2 in the rules. And finally, there are BMPs in chapter 11, and those are not GI. So that's how we break up all the new reference numbers to the BMPs. So pre-treatment is an important design criteria now. And if you don't see it under basic design criteria, then it's probably listed under the type-specific design criteria in that chapter. Now, roof runoff can be treated by certain measures that are listed here, and on pages 5 and 6 of the cistern chapter, you'll find more details. These are the graphics that were taken from chapter 9.1, leaf screens, first flush diverters, and roof runoff. Okay. So the requirement for pretreatment of roof runoff can be waived under the conditions that are listed here. So a building that is significantly taller than any surrounding trees and doesn't have a vegetative roof should not need the pretreatment. However, in making this determination, the review agency must consider the mature height of any surrounding trees. Now, if you're going to use another BMP for pretreatment, it must be designed in accordance with the design requirements in its respective chapter, and you're always going to check the BMP manual for the specifics. Remember that roof runoff that is commingled with surface-generated runoff must be treated per the manual. For subsurface infiltration basins, pretreatment may consist of any of the BMPs found in the manual, and 80% TSS removal must be the pretreatment that is provided. small-scale bioretention systems designed to infiltrate that have flow entering as sheet flow or overland flow can alternatively use a 5-foot wide gravel or stone strip to filter runoff instead of some of the other forms of pretreatment. So that's it for pretreatment. Let's go back to exfiltration. And actually, where can't you use it? Basically, BMPs with an under drain. So for those sites that are in special areas or that have no runoff leaving the site, exfiltration can be used for the entire storm under these conditions on this slide. This is also taken from the chapter. You must determine which is the maximum storm for which no runoff leaves the site in the existing condition, or if infiltration of the entire storm is required by a law or is a rule established by, say, the Pinelands Commission, the Highlands Council, or another stormwater review agency that has jurisdiction over the project. So groundwater mounting analyses are required when using exfiltration in the routings, and these are the conditions that also apply. Basically, soil must be tested in accordance with Chapter 12, and you must follow Chapter 13, which is specifically about the analysis methods that are to be used. Additional things that you need to know about groundwater mounting. The mounting analysis has determined that an adverse impact will occur if the resulting groundwater mounting reaches the bottom of the BMP, or if the temporary localized increase in the water table encroaches upon a building or another structure, including any septic systems. So when an adverse impact is the result, further modifications to the size of the infiltration area of the BMP or reductions in the exfiltration rate must be performed until the adverse impacts are eliminated. So groundwater mounting that reaches the bottom of the BMP means that the hydraulic gradient is reduced. So the BMP can't infiltrate as fast as originally expected. So you're going to have to redo the routing calculations to calculate new peak flow rates. And I'm not going to run through that here, but do read examples 5.6 and 5.7. They start on page 44 of chapter 5 for the methodology that is used. And you'll see more about groundwater mounting as a presentation in module 3. It's also mentioned in how to review a project, and we'll take a little bit deeper view of it at that time. And so meanwhile, we have to finish out the rest of chapter 5. Which brings us to the rational method, as I promised, because it's still in the rules for now. All right, so as I said, it's been around since 1889. It's a simplified method, and how it should be used are based on certain assumptions. One is that the rainfall event is the same everywhere in a drainage area for the duration of that particular rainfall event, and almost everything is assumed to be uniform: ground cover, soil type, slope. And you must always check that that assumption is valid. That's something that's often oversimplified. Secondly, the maximum runoff rate occurs when the rainfall duration lasts as long as the time of concentration. So that means every point in a drainage area is contributing runoff. Lastly, the frequency of rainfall and runoff are equal. So a 2-year storm will generate a 2-year flow, assuming everything else is equal and constant throughout this drainage area that you're looking at. Now, the BMP manual says the use of the rational method should be limited to drainage areas that are less than 20 acres in size with uniform surface cover, soil type, and slope. So it's used for urban areas, but it's not applicable if areas of ponding occur within the drainage basin, and the method can only be used to calculate peak flows. So the rational method equation, Q equals CIA, can only determine a peak flow rate. Q is the peak flow in cubic feet per second. C is the dimensionless runoff coefficient. You can refer to table 5-3 from revised chapter 5. I is the intensity in inches per hour for the time of concentration of the drainage area, and A is the area in acres. So if you look at this, you might think that it's not dimensionally correct. So although I is in inches per hour, 1 inch per hour is actually equal to 1.008 cubic feet per second per acre. But when you're using this equation, the two were basically taken to be numerically equal, so no conversion factor is required. Okay, So one source, as I said, for runoff coefficients is table 5-3 in the new version of chapter 5. And the runoff coefficient relates the percentage of rainfall that will become runoff. So less runoff is produced by forest than pavement with the same slope. And we recommend using a value of 0.99 for impervious surfaces, as this is conservative and will best represent what will actually occur. So if you see 0.95, that can make a difference. So look for that in your calculations using the rational method. So we also calculate the time of concentration in the same way as the Nrcs methodology, but we also need to determine the rainfall intensity. So when you're reviewing your calculations using the rational method, check the rainfall data. If you're going to use the NOAA data server, make sure that you have the intensity tab checked. So this is for the DEP headquarters in Trenton for a 2-year storm with a time of concentration of 10 minutes, and we get 3.92 inches per hour for our 2-year design storm. So if you don't like tabular data, you could also do this. You could use the IDF curves shown in the NOAA data. And why do we use this? Well, rainfall intensity is the average rate in inches per hour for a duration equal to the time of concentration, subject to a minimum for a selected event. Once the recurrence interval has been selected for design and a time of concentration calculated, rainfall intensity can be determined from these curves. And Chapter 5 also includes more information on using this. So identifying the proper duration and intensity to use for design purposes is very important, and I'll get into that in just a second. And I promise you, we're almost done. So the rational method calculates only the peak flow for a specific storm event and not a runoff volume. And it's often used in sizing your MTDs based on peak flow rate. So for the New Jersey water quality design storm, the rainfall distribution is not evenly distributed over the entire duration. So using an average intensity of 1.25 inches over 2 hours, meaning using 0.625 inches per hour, cannot be used as the value for rainfall intensity in the rational method equation. Okay, the minimum time of concentration that may be used is 10 minutes. Why? Because that's what's here at the left end. Okay, for the water quality design storm, the corresponding intensity is 3.2 inches per hour, not 0.625. So make sure your correct intensity is used when sizing your MTDs, and this will also be covered in Module 3. So if you haven't read it, Chapter 13 includes a lot more examples on groundwater mounting, and I'll do a couple of them in Module 3. And even Chapter 5 has been revised to include examples with groundwater mounting analysis and includes exfiltration in the routings. So if you need to get in touch with me, I'm sure you know my information, but it's here. And at this point, I'll ask if there's any more questions for this presentation.
Nothing in the chat right now.
Okay. So then,
Oh, we do have one question.
We have a question.
Yes. Should the modified rational method be used in the post-developed conditions to determine the critical volume required within the BMP?
If you're using the rational method, you need to use the modified to come up with the critical volume. They work in tandem. Jenny, do you want to weigh in on that?
I'm reading the question. Should the modified rational method be used? For the modified rational method, the rule says you can use that to determine the storage of the for the BMP, but it's not necessary. You have to. So
yeah, no, have to. But if you're using the rational method and you need the critical volume, then you use the modified rational method in tandem with it. And you can continue to use the rational method. It's in the rules that it's allowed. All right, so that should answer the other question, which should the rational method be used after the March 31st date? I assume you meant March 2nd, but it's still allowed in the rules. Okay, we are 10 minutes over, although we did start late. Let's see. Shall we take our break now, Changi?
Yeah, I think we schedule a break, so let's take a break and then continue for next presentation.
All right, it's 11 minutes after 2. What time should everyone be back?
And I think we can give like 5 minutes.
Okay.
Around 5 minutes.
All right, so everyone be back at 2:17.
Ms. Schaefer,
Yes.
Steve Reiner's here.
Hey.
I have something at 3:30, so I'll be signing off at 3:30 today.
Okay, do you have the ability to enter that in the chat when you do go?
The problem is I don't see the chat.
Oh, okay. All right.
On my mobile phone. And when we go to take the quiz, I'll probably ask you if you can send me the link again like you did the last time.
Oh, okay, yeah, we probably won't get to the quiz by then, so
Okay.
we'll make arrangements to send you something separately. And then we'll review your answers with you, probably through email, okay?
You got it. Thanks.
All right, so you're gonna leave at, you said 3 o'clock?
3:30.
3:30, okay.
Yep. And I'm not a PE, so I don't get any PE credits or anything like that.
Oh, okay, all right, that's great.
Thanks.
Okay, I appreciate your letting us know. And I'll make a note of that. Thank you. Okay, the time is 2:20. We actually ran a little over on our break. We'll get back underway in just a moment. Please stand by.
Okay, welcome back from the break. I will be going over soil testing requirement for this presentation and what is necessary to be complete as part of stormwater management report for a major development project. And just a note that NJBMP Manual Appendix E has been updated and issued as NJBMP Manual Chapter 12. So please look into our website and download the new Chapter 12 for your reference. And before I get started, it is important to mention that as part of our audit inspections, soil testing is one of the areas that we often find to be done incorrectly. And what is soil testing? There's a misconception that only infiltration BMPs needs to perform soil testing for soil permeability. Actually, soil testing means more than just soil permeability. Soil testing, including finding the correct hydraulic soil group, season water height table, soil permeability, and the soil series for annual groundwater recharge. As Lisa has mentioned, that the identification of correct hydraulic soil group is essential to have an accurate calculation for the volume and peak flow rate of runoff, regardless whether you design infiltration or other type of BMPs. Also, many BMPs require separation between the bottom of the BMP and the seasonal high water table. For example, the lowest elevation in a service extended detention basin must be at least 1 foot above the seasonal high water table, excluding the low flow channel. If you don't have a soil testing report showing the depth of the seasonal high water table, you will not be able to judge if the design criteria has been met. Finally, if you use groundwater recharge spreadsheet to calculate the annual groundwater recharge and the deficit, you will need to know not only the hydraulic soil group, but also the soil series of the site. So let's address each topic in the soil testing. First topic we want to talk about is the finding hydraulic soil group. The classification of the hydraulic soil group for soil is used to determine the runoff curve number developed by the Nrcs in the revised Chapter 5 of the BMP manual. Also has a table for various runoff coefficients for rational method, and which is indexed by the type of land cover and the hydraulic soil group. There are 3 methods to identify the classification of the hydraulic soil group. The first one is from the Nrcs web soil. Second one is deform method, and third one is actually perform soil testing on the site. And the first method is just very simple. It just goes through the web soil survey. And you might have seen the soil survey report that attached to the stormwater management report you reviewed. And why do we have to show you how to get the soil survey report? Because sometimes there's no soil report attached, and sometimes the information is not sufficient, or the soil report of the wrong site is attached. So it's always a good practice to double check the soil survey, and you will not take too much time to get the soil survey report from Nrcs website. And there's a note that we have seen paper-based soil survey report being used in stormwater management report. And please note that we have checked with Nrcs about the paper-based soil survey report. And Nrcs said that they have stopped updating the paper-based soil survey report. So the most updated information is on the web. So please stop using paper-based soil survey map unless you have checked that the information on the paper-based soil survey map are the same as in the web soil survey. So let's take a look of the Nrcs web soil survey website. So you click on the Start WSS, and it brings you to the map. And then you can begin with the AOI, that's area of interest, and the soil data explorer that's being circled on the screen. Has the soil map data for covering 95% of the nation's counties. So you would get the information of the soil map for the site, most likely. And after you get the into the details, and you select the soil data explorer, and then select the soil properties and qualities to find the hydraulic soil group. And then after that, selecting the hydraulics data explorer tab, then and the soil properties and qualities sub-tab. You select the tab on the left, soil quality and features, and then have the HSG, and then you select view rating button, and you will see the table listing the hydraulic soil group for the soils within the selected area or the area of interest by soil mapping unit. And so as that shows that there's a different boundary of the soil mapping shown on the screen. But if you don't see that the hydraulic soil group for a specific soil mapping unit, it means that there's no determination of the hydraulic soil group. So it often happens in urban areas where soil mat has been disturbed or that's been filled with construction materials. And when there's no hydraulic soil group rating for the specific soil mapping unit, then you may have to determine by next methods like default or the soil testing on the site. And for the soil in dual hydraulic soil group, such A/D, B/D, or C/D, the first letter applies to the drained condition and the second applies to undrained condition. The appropriate choice of the hydraulic soil group would depending on whether or not the site has been drained. So further investigation is necessary. You may have to do the soil testing on the site to figure out the season high water table. And one more thing I would like to note is that if you know that site is being filled with constructed material, debris other than the material than soil shown in the soil survey map, you may not solely rely on the hydraulic soil group information shown in the soil survey. You may have to really do some soil testing on the site. And this is the second method we address in chapter 12. You don't have to do the soil testing. You don't have to check the soil map. You only have to determine whether the project is in coastal plain or not, or outside the coastal plain. And for the pre-development condition, you always use the A soil. And for the post in coastal plain, use soil D. And for outside coastal plain, for the pre-development condition, is soil B. And then for the post-development condition, is soil D. And for the determination of whether the project is in the coastal plain or not in the coastal plain, there is the physiographic province of New Jersey map in our chapter 12, but it also available, has the GIS data available in our DEP's GIS department, and you can follow the link and to download the GIS data if you have the GIS tools. And next one is that if you don't want, you cannot use method 1 or 2, then the third method is to conduct the soil testing to identify the hydraulic soil group. And the soil testing to determine the hydraulic soil group must perform the saturated hydraulic conductivity, or we said the soil permeability. And you have to find the depth to the season water table, the depth to the impermeable. And the result, you have to look up the table in the National Engineering Handbook, Part 630, Chapter 7, Hydraulic Soil Group, and you can find that those information and to map the correct hydraulic soil group. And we have some criteria for taking soil testing on the size of the soil mapping unit. Use the table, it gives you how many soil profile pits and how many soil borings you have to perform for different sizes of the soil mapping. And please remember that this table is for the soil profile pit and number of soil borings for determining the hydraulic soil group. We have another table and criteria for the soil profile pit that had to be performed for taking the soil permeability rate. And we will discuss about the table later in our later slides. And here is one example for the soil profile pit and soil boring locations and numbers for that for the site has 2 soil mapping units. The purple one, there is soil mapping units of unknown soil. That is 2 acres. So you will have to have 1 soil profile pit and 4 soil borings because it's 2 acres. And for the green area, there is another soil mapping unit, and it has 6 acres. So because it's greater than 2 acres, so according to the table, you will need 3 soil profile pit, and then you have need 4 soil boring for the first 2 acres, and then have another 2 soil borings for another additional 2 acres. And here is the next requirement is the depth. For the depth of the soil profile pit and soil boring depth in each location, that is for the determining of the hydraulic soil group is at least 14 inches below existing grade, except when the seasonal high water table is at a depth of 24 inches or less. So when you have the soil profile pit is excavated into the subsoil, if within 24 inches that you encounter, you determine that the seasonal water table is less than 2 feet, then you can stop the excavation and determine that would be, later we will say that would be a D soil because the is an undrained condition. And so just note that the you have to also perform the test for saturated hydraulic conductivity of the most restrictive soil layer above the impermeable soil layers. And also, as I said, you have to determine the depth to the seasonal high water table. And we want to note again that in the previous Appendix E, it was say that you have to go down 6 feet above the seasonal high water table. And the new Chapter 12 has already revised the depth requirement. It's only the minimum is 40 inches. And although you can go deeper, but the minimum is only 40 inches for a new Chapter 12. And all the depths and also those soil classifications must be included in the soil log. And here is the table, as I mentioned earlier, the Chapter 7 of the National Engineer book. And there, the table is small on the screen, but you can go to the follow link to get the table. And you will know that the criteria determine the hydraulic soil group by the depth to the impermeable layer, to the seasonal high water table, and have the conductivity rate. Then you can know the classification of the hydraulic soil group. And here is one example of the soil log in figurative presentation. So after we determine the hydraulic soil group, we want to talk about the soil testing for infiltration BMP. And the infiltration BMP, what we mean for that is that a BMP that infiltrate runoff into subsoil, including, for example, infiltration basin, sand filter, bioretention basin, pervious paving system that designed to infiltrate runoff into the subsoil. So the requirement for infiltration BMP is that a minimum of 2 soil profile pits must be excavated within the infiltration area of any proposed infiltration BMP. Then you have to determine the elevation of the seasonal water table and to test the hydraulic conductivity of the most restrictive horizon between the basin bottom and the season high water table. And you have to place the test pit must be sufficient to provide adequate characterization of the infiltration area. And what we're doing means the infiltration area, we means the bottom of the basin, not including the side slope. Sorry. Then if for the infiltration basin larger than 10,000 square feet, then a minimum of 1 additional soil profile pit must be conducted for each additional area of 10,000 square feet. So you have to remember this number, and at least 1 test to establish the soil hydraulic conductivity must be conducted for each soil profile pit. So to verify the location and numbers of the soil profile pit for the infiltration BMP, you need to see a site plan depicting the location of the lost soil profile pit that are within the infiltration area of the proposed BMP. And here is one example. And this one, you can see that the infiltration area is 25,000 square feet. So, as we said that you need to have 2 for the first 10,000 square feet. So 2 soil profile pit for the first 10,000 square feet, and then have 1 for additional 10,000 square feet, and another 1 for the extra 5,000 square feet. And for the in the new chapter 12, we have more requirement for the small scale GIBMP, as known that those GIBMP may be small in size and then distributed around a development. So the requirement is that you need 1 soil profile pit for each soil mapping unit where the multiple BMP are located, plus for each BMP, infiltration BMP equal or less than 500 square feet, you need 1 soil boring at each BMP. And then for each one BMP that's greater than 500 square feet, then you need 2 soil boring at each BMP. For the small scale GIBMP located linearly, that means that along a street, you have multiple locations that have the GIBMPs. Then you will need 1 soil boring at each BMP and 1 soil profile pit for every 2,000 feet in the linear along the linear location of the BMP. And just note that for each soil boring at those BMP or 2 soil boring at the DMP, you need test at least in one location of the soil boring for the hydraulic conductivity rate. And we have another kind of the infiltration BMP. For example, the bioretention swell, and that has the infiltration area length to width ratio is equal or greater than 4:1, and the bottom width is 25 feet or less, and then the top width is 40 feet or less. For this kind of the linear infiltration BMP, that you need one soil profile pit for the first 500 feet, and then another soil profile pit and also one boring per 500 linear feet for the additional 2,000 feet. So here's another example for the linear infiltration BMP. On the top, there are two soil units. The first soil mapping unit is 500 feet. So you only need one soil profile pit. For the soil mapping unit next to the first one is in green. The length is 2,000 feet. So you will need one soil profile pit and then have 3 soil borings following the soil profile pit. And for the example on the bottom, it's just one soil mapping unit. The length is total 2,500 feet. So you will need one soil profile pit and then 3 soil boring, but now you will need another soil profile pit because it has greater than 2,000 feet. And for each soil boring or soil profile pit on that location of the testing, the depth has the specific criteria. If there's no soil replacement, then the depth of the depth to test the most hydraulically restrictive soil layer below the BMP and above the season high water table, you have to is the soil layer between 8 feet below the lowest point of the basin or 2 times of the maximum water depth. If there is a soil replacement below the proposed BMP, then you must perform the test on the most hydraulically restrictive soil layer below the depth of the soil replacement and above the season high water table or bedrock, and then the depth is 8 feet below the lowest point of basin or 2 times of the maximum water depth, whatever is greater. For the testing method for determining the soil hydraulic conductivity, acceptable hydraulic tests including the tube permeameters test, percolation test, case borehole infiltration test, single ring infiltration test, basin flooding test, and for the also the ASTM D3385 double ring infiltrometer, and USBR. They have well permeameter, and then other soil testing that have the in situ condition and are accompanied by a recognized published source reference. For example, we like ASTM, Nrcs, and also like the Soil Science Society of America. Their publication are all being we will consider that as a recognized published source for the testing method that being determined suitable for testing hydraulic conductivity rate for determining the permeability. also for the soil exploration, when you use the soil boring, then you have to follow STM method to get the soil boring. And also, as we said, that you may take the sample to determine, if you use the boring to determine the soil layers, the sampling must be continuous for the entire depth of soil boring to full characterize the soil profile. So in some cases, if you cannot do the soil profile pit, you have to use soil boring. Then the soil boring, as I said, that must be continuous, so you can know the whole soil profile pit, whole soil characterization in the depth. And in our new chapter 12, we have 6 methods being described in details that have the detailed steps, and also the equations and the worksheet that help you to determine the proper hydraulic conductivity rate for the soil you tested. And for those methods we mentioned and not have the detailed description in our chapter 12, you may reference those ASTM method, or as we said, that the recognized source, probably that for the detailed steps. And one thing I would like to mention is the percolation test. There was one table in Appendix E have the conversion of the percolation rate to the hydraulic conductivity values. And we have the correction of those values. And also, I want to emphasize that although in the test step 4B, in the test procedure for the percolation test in 12, require water be filled to a depth of 7 inches, and the time recording should be being recorded for the drop of 6 inches. But in the actual test, you should fill the water to 7 inches and see it drop to 6 inches and start the clock, and then measure the time between the 6 inches to the empty of the water in the test hole. And next topic is the soil testing for the season high water table. And there are 2 major methods that you can use to determine the season high water table. One is the observation of the reductive morphic features of soil modeling, and you can do that in any season of the year. And second method is the direct observation of the season high water table, and that can be done only between January to April. But if you want to do the direct observation of the season high water table, then you can use the Nrcs Web Soil Survey, and in that survey, it provides the season high water table. But you have to check the soil series presented at the site is identified based upon the comparison of the soil profile morphology observed within the soil profile pit and the soil profile description provided in the soil for the soil series in the Nrcs web soil. So in summary, that is that you have to see the soil layers, soil series identical in the soil, the Nrcs web soil survey and the field soil testing, and you have to see that identical. Then you can use the information of season high water table in the Nrcs web soil survey. And those soil testing I just mentioned for the soil testing before the construction, and for the soil testing during the construction and post construction. During the construction, you have to minimize the compaction. If there's an infiltration BMP, you don't want to have the big machine driving on the bottom of the basin. And if you put if you put the soil into the basin, you have to make sure that each layer that where the hydraulic conductivity is critical, you have to know that it's not minimized or to have any adverse impact to the permeability of the basin. And for the post-construction, then you have to do the same testing, the number of testing, same as the pre-construction test. But because you already have the basin being built, so it's not necessary you have to excavate the soil to the most hydraulic layer to do the test. Instead, you perform the hydraulic conductivity test on the bottom of the acidification of the BMP before sand and soil layer is placed. And only single ring, double ring, basin flooding tests are allowed. So basically, you don't dig the hole into the basin that's been built. You just test the soil on the bottom of the basin before the sand or soil bed is placed. So for the soil testing, what should be submitted? As we said, that the web soil survey showing the hydraulic soil group must be submitted. So you will be able to identify the proper soil associated with the curve number or even the runoff coefficient. And you have to see the location of soil profile pit and soil boring, whether that follow the criteria in Chapter 12, and also can properly identify the soil characterization of the infiltration area of the whole site. And also for the soil test log, you have to know the date performing the soil profile or boring, which is important to determine whether appropriate method to identify the season high water table has been used. You have to know the elevation of the existing ground level, so you can calculate whether the depth of the soil profile pit is sufficient. So one thing I want to know that we have seen a lot of the soil profile being claimed that being in proper depth is measured from the existing ground level, but as you see that the requirement for the soil profile pit depth for infiltration BMP is measured from the bottom of the basin, the proposed elevation. So even though they have the 8 feet depth of the soil profile acidification, but that is measured from existing ground, so it will become insufficient to meet the requirement that has to measure from the bottom of the BMP. And also for the soil test log, you need to know the soil classification and description, the soil series, and then you have to know the most important one for the infiltration basin BMP is that where the depth of the soil, where the soil hydraulic conductivity test is performed. And then you have to know the method of the season high water table determination. And then for the hydraulic conductivity testing, you need to have the testing record showing the time, the dropping depth, and so you can verify whether the procedures, and so you can verify whether the testing has been performed correctly. So here is my information. Do we have any question?
Yes, we do. All right, so first one here is, can you please clarify when soil testing is required? What is the site? What if the site is already developed?
For the site that has been developed, you still have to determine the hydraulic soil group for those areas that's been in the pre-construction condition that is not covered by impervious surface. Also for those areas that in the post-construction condition, that is going to become pervious area. So you need those information to determine the curve numbers. So that the curve number is determined based by the hydraulic soil group. So you need those testing. And also for the proposed basins, you definitely have to know the hydraulic conductivity rate for the most retrieved soil layer below the basin. So you have to test those areas too. And if you have the BMP that is not infiltration to the subsoil, you still have to know the seasonal high water table below the proposed BMP. So there's still a lot of testing required for a redevelopment site.
Another question is the number of profile pits required based on the total site area or the proposed disturbed area?
It's depending on the number of the soil profile pit, whether that is being performed for determining the hydraulic soil group, or that is being performed for determining the hydraulic conductivity rate of the soil for infiltration BMP, or the season high water table under a BMP. So it depends. So you have to look into the tables we just present, and also the chapter 12 to determine the numbers of profile pit according to the different purpose for the soil profile pit.
Another one is soil testing required for all stormwater management calculations?
As we presented in the first slide, soil testing means a lot, means the determining of the hydraulic soil group of the site, and determining the seasonal high water table, determining the hydraulic conductivity rate. So depending on what calculation you are talking about, if you want to for the calculation of the runoff from the site, then you would have to know the hydraulic soil group for to determine the CN number, or to find the right index for the runoff coefficient. So you have to test the soil too, find from the soil survey. For the calculation of the infiltration BMP, definitely you have to know the hydraulic conductivity rate for the soil underneath the basin, the proposed BMP. So looking into chapter 12, you have the clear explanation and table to show that what soil testing is needed for what kind of which purpose, and you will know that how many testing you have to do for a site.
Another question here is, if the soil classification is the same soil series with a different erosion class, are additional test pits required?
I have to look into this question, so we will get back to you for this one.
Here's another one. Using soil CHCB as an example, the typical profile exhibits a seasonal high water table of less than 24 inches. How is the soil testing completed then?
If you have the season high water table less than 24 inches, it will be automatically determined as D soil according to the National Engineering Handbook. So I don't know if what other testing you mean, but if you have already have that determined less than, but you have to before you determine the season high water table is less than 24 inches. As I said, that the determination of the season high water table, if you want to do that by using Nrcs soil map, then you have to have identical soil series that you can you find in the from the field soil testing, and also matching that in the soil map. Otherwise, you have to perform the soil testing on the site, either by direct observation of the season high water table between January to April, or you have to use the reductive morphic features of the soil to determine the season high water table.
Next question here is regarding soil testing. Where should it be tested in case of pierced groundwater? Also, for design of a 10-foot pond, in what depth should the hydraulic conductivity be tested?
For the determining of the pond, a wet pond, is that the question asking?
Yeah. Yep.
For the determining of wet, for the wet pond, because the design criteria for wet pond is that you have to determine the soil is not very permeable, and I think there's other criteria in the wet pond, whether regarding the season high water table. So you have to perform the soil testing in accordance to the description design criteria in the wet pond. Please check the wet pond chapter.
Is soil testing for HSG determination required for all project, or is it only when site conditions contradict the web soil survey?
As we said, that if you have the soil map from the soil survey web soil survey, that can determine the hydraulic soil group for the site. For each soil mapping unit, then you may rely on the soil survey's information. But we have the note that if you knew the site, that the soil is not like what is described in the soil survey map, in the soil survey, then you probably would like to determine what is actually on the site, what kind of soil actually on the site. So you would have to perform, either you can use the default method for the soil group, or you can perform field soil testing to determine the proper hydraulic soil group.
Another question here is, when the soil survey indicates a soil with a dual hydrologic soil group, which HSG should be used for runoff calculations?
That would depending on what we say about the season high water table. If you determine the season high water table is less than 24 inches, then the soil would be classified as D soil. Then you use D soil to in the calculation. But if the season high water table is less than is deeper than 24 inches, then you will be the other side of the soil group.
Another question here is, if soils below an infiltration system are being replaced to the depth of the seasonal high water table, is hydraulic conductivity testing below seasonal high water table or of surrounding soils required?
if you determine, although I don't know whether that would be in the case, if you determine to replace the soil from the bottom to the seasonal high water table, and there's no any restrictive soil layer between your lowest point of the soil replacement and the seasonal high water table, then you may not have to test any soil because the runoff will be infiltrated through the replaced soil and then directly to the water table.
How do we determine by looking at a soil profile which is the most hydraulically restrictive layer where the permeability test should be taken?
I think from the soil log, you can see that you may have the clay soil, you have maybe a CLT soil, and that the soil technician of those professionals, they would know relatively which soil layer is more restrictive than others, so they can determine which soil they have to perform the hydraulic conductivity test.
For the seasonal high water table, is there an exception if the area is in the tidal area?
No, not I can think of.
If a test pit is excavated between January 1st and April 30th to enable direct observation of the seasonal high water table, but the observed water elevation is deeper than mottling, which is the correct depth to the seasonal high water table?
That's a good question. I have to look into it and get back to you.
Okay. Is the pit bailing test no longer acceptable to determine the soil permeability rate?
Yes, because the pit bailing test, if you look into the detailed steps, it's testing the soil in the water, in the groundwater, below the groundwater level. So the requirement for the hydraulic conductivity rate of the soil is for the soil above the seasonal high water table. So that the test has been removed from our chapter 12.
What is required if in-field soil testing reveals that soils are acting as HSG-D soils though mapped as HSG-A, B, or C soils on the web soil survey?
Yes, we said that if the field testing determine the soil is not what it shows in the soil survey map, I think you probably would have follow the soil testing, but in the caveat that the soil testing has been done correctly according to our chapter.
What about redevelopment projects where stormwater management is met through a reduction of impervious surface and no structural BMPs are required? Can the web soil survey classification be used in that specific instance?
As we said, that the soil testing means a lot, means determining the hydraulic soil group of the site, means the seasonal high water table, means the infiltration, the permeability rate. So for the permeability rate is only required for the infiltration BMP. So if you don't have any BMP proposed, then you may not have to do the soil testing for infiltration BMP, but for determining other factors, you may still need the soil testing. So it would be depending on what you need to look into and what information you need, what soil information you need to determine whether that you need the soil testing for the project.
And just a couple more. Is the soil permeability class rating test no longer allowed?
I don't exactly know the question, but Dinesh, I think we kind of run out of the time. Maybe for other question we can answer, get back to those attendees, offline. So I think I would like to hand over the time to next topic presented by Dick McGee.
Are
All
we
right, thank
taking-
you.
We're going to go straight
I'm
in
here.
without a break, or what are we going to do? I know you're
I
here.
think
Dick.
Mr. McGee already ready
Right.
to present, right? So I think we will just go straight to his presentation.
Okay.
Yeah, I will try to, because I realize you're running out of time. I will try to shorten my presentation, highlighting it, recognizing that people can read some of the other stuff, and we can then move on. We can then move on accordingly. So I'll do my best to try to, because I know you've got to allow time for an examination, a quiz. So.
Mr. McGee, you can just present as you planned it. We can arrange the time in the quiz, so no problem. You can just present as you want. Yeah.
Well, okay, all right. I was trying to be helpful, but if we can do it, I'll still try to. Shanghai, I'll still try to get to move it along here. It's been a long day, a lot of material. I'm impressed. I've sat here and I've listened, and it's been very educational for me. I guess I need my next slide up, or I need my first slide up.
Anthony?
I don't see anything.
No, hold on. I'm just figuring out, I think someone was planning on having it.
Okay, just a sec. I can pull it up, Lisa.
Okay, great. Thank you. And there we go.
Yeah, here we are. Okay, let's begin. Again, thank you for inviting me. I'm here to talk about New Jersey Corporation for Advanced Technology. I think many of you may have heard about NJCAT, but today I want to stress the relationship that we have with DEP dealing with stormwater manufactured treatment device, what we call MTDs, as you know, verification certification program. And I want to point out that this is a partnership between NJCAT and NJDEP, as you'll see as we move along. All right, I'm going to go quickly so you have it. First thing we're going to look at, next slide, we're going to look at a little bit about the history of where did NJCAT come from, how does it fit. This really goes back to the late 1990s when discussions between former Governor Florio, former Commissioner Robert Shin, and then President of Stevens Institute of Technology, Hal Ravichet, decided there was a need to have some mechanism to develop and promote innovative energy and environmental technologies, what we call IETs. The law, which came out of it, Public Law 1999, Chapter 400, basically is called the EET Act, and defines the roles and responsibilities of the state of New Jersey, DEP, and NJCAT. Next slide. An equally important document which came along about 6 months later, June 6, 2000, was a performance partnership agreement, which was executed between NJDEP and NJCAT. And not to go through all the details, you can read the words as well as I can read them to you. In the middle of this slide, you'll see that DEP is required to consult and work with NJCAT to develop performance evaluation, verification procedures, processes, and protocols, okay? And this is to determine the application and use of certain IET in the state of New Jersey. Next slide, which is probably something you know. Obviously, US EPA requires stormwater compliance. Various states have adopted strategies to accomplish this. Low impact development strategies obviously seek to reduce or prevent adverse runoff. We've been talking about that. And basically, these become known as sound site planning, or a subset of practices known as best management practices, or BMPs. Next slide. Now, I mentioned to you earlier, we're talking about best management practices. These are a subset of BPMPs, okay? They're not the sole answer. They're another tool in the toolbox. And again, for a definition viewpoint, MTDs are proprietary, prefabricated stormwater treatment systems that rely on a variety of mechanisms to remove pollutants from stormwater. Obviously, the major pollutant that's focused on here in New Jersey is sediment removal. You can see here, you can use settling, filtration, you can use absorption, adsorption media, vortex, a whole lot of vegetation, whole lot of different ways that MTDs are designed. They're engineered systems that are designed to manage and treat stormwater runoff. Next slide. In here, obviously, you know major projects develop 80% removal. You know that. Second bullet down, you know the state is moving to a large dependency on green infrastructure BMPs. And there are 3 criteria, and this is becoming where my role is changing. More and more of the manufacturers are bringing in MTDs that they hope to meet the requirement of green infrastructure. I do not verify for green infrastructure. I verify that the technology can meet sediment removal. And then DEP makes an independent determination of whether or not it fits your criteria for a green infrastructure. And you know there are 3 of those. You either treat stormwater through infiltration into the subsoil. Very difficult to do it practically with a manufactured treatment device. You treat stormwater through filtration by either vegetation or soil, or it could be vegetation and or soil. And in some limited cases, people use, they treat stormwater runoff for reuse, for gardening and other things as well. But when someone comes in with a GI, if they want a technology, one of the things we check to make sure it's going to meet that criteria. Obviously, your NJAC 7.8 provides approved TSS removal rates for both BMPs and MTDs. And the TSS removal rates for MTDs come about through this joint program, this partnership between NJCAT and NJDEP. I always say NJCAT verifies performance, NJDEP certifies. And we'll talk more about that as we move along. Next slide. What is this technology verification program? Well, it's an independent third-party evaluation program to verify the performance claim. You as a manufacturer, you as a innovative environmental or energy technology. By the way, we do more than stormwater for DEP, but that's the predominant business. You say your device can have a certain performance. That's going to require some testing, and we've talked about the protocols before. And we verify, in fact, that the testing has met the protocol, the performance has been verified, and then it moves on out for certification. Important thing about this program, the NJCAT, NJDEP program, it has strong national and international recognition. It has become like the UL of MTDs. We get inquiries, and I'm supposed to get a visit before the pandemic from Australia. I've got 2 technologies that are coming in any day from Germany. I've got a couple technologies that are being tested in Canada, and there are quite a few technologies that are being tested across the country. I want to make a point, however, that this is a laboratory verification program. You may have heard about the TAPE program, which is a program run by Washington State. That is a field verification program. When New Jersey started this process back in the early 2000s, were in a partnership with 6 other states, and it was to do field verification. It became apparent the difficulty of doing field verification because Mother Nature does not always cooperate and give you the condition you'd like to verify performance. So about 2009, the department made a decision. They were going to sunset that field verification program, and they were going to go to a laboratory verification program. What that says is it's obviously you have to use a surrogate for a sediment, but you can control your flow rates, your sediment dosing, and you can get a really good profile so you can compare one technology to another. So stormwater MTDs are evaluated against 2 existing NJDEP protocols. They're your protocols. They're not my protocols. NJCAT administers the program. The 2 types here are hydrodynamic separators, and that protocol has just been updated this year, and we'll talk a little bit about that, January 1st, 2021. And you should note that any hydrodynamic separator that is verified and certified in New Jersey will only certify for a TSS removal rate of 50%. So when you see plans coming or other things saying TSS removal of 80%, which some people do with a hydrodynamic separator, that is not a certified technology. If you have a filtration treatment devices, that, and we'll talk a little bit later, that has not been updated since January 25th, 2013, because it's working pretty well, but it does need to be tweaked, and we hope to do that this year. In those cases, you can get removal rates of 80%. So even if you demonstrate that you got 90%, you still only get 80% credit. Here is key to you as you look at these. Only stormwater MTDs that have been verified by NJCAT and have been certified by DEP are the only MTDs that can be used to satisfy the requirements of the stormwater management rules or rules for major developments. To date, that number is going to change quickly because one just got certified today but hasn't been posted yet. Hydrodynamic separators, they're 18. Filtration devices, 11. Green infrastructure, 7. I want you to note, and again, I'll repeat this, that all hydrodynamic separators have a sunset clause and that are currently certified. And that's because the new protocol that came in January 1st of this year, we believe is an improvement in comparing performance and ensuring, in fact, that water quality is maintained. If you go to the website, which is listed on the bottom there, you can look at you can find all of these technologies that are in these various categories. Next slide. Oh, I was going to stop at that point. Are there any questions about the program? If you're not familiar with it, I'd be happy to answer those. People are getting tired or I spoke too fast. All right, I want to go quickly through 3 technologies just to give you an idea of the variables. This is a kind of a vault type technology where the storm water flow comes in from the left-hand side. There's got a debris ramp up there, which then directs, as you'll see in the next slide, into a trash rack. In there, you'll see it over there. So you collect trash on either side. Meanwhile, the stormwater that is not trash will go through and will settle out below in those areas in the chambers that are beneath there. And then we'll go out in the outside and we'll move to the outside of the debris separating baffle box. When these units are tested, they're tested one with an inlet concentration of approximately 200 milligrams per liter. They're tested against a very stringent sediment particle size distribution as specified by New Jersey. And they're tested at 5 different flow rates up to the what's called the manufacturer treatment flow rate, which is the one that you would design towards based on all the other material you've learned this afternoon about how you calculate stormwater requirements. Also, to ensure that these devices will not scour out, particularly if they're online, they have to run a scour test. The scour test fills up the sediment sump to 50% of the maximum storage capacity, and you have to demonstrate that you do not take out sediment at a higher rate than 20 milligrams per liter in the effluent. So we do the best. The protocol is set up to do the best we can to ensure that these will work in the field. One of the things I want to point out here, this unit is tested. You'll notice to the left-hand side coming with a pipe, the right-hand side coming out, and these pipes are what? These pipes are aligned. You'll see not so much in this type of a design, but you'll see people coming in with different configurations than what was tested, and that's a no-no in the sense that performance has not been certified and cannot be used in the state of New Jersey. Next slide. This is one of the first green infrastructure technologies that are coming in. It's called the Contact Filtera High Capacity. They have an earlier unit called Contact Filtera. But for example, here what you see is maybe off of a gutter inlet, the stormwater being directed into the manufactured device. It's designed to have some type of a planting in the middle. If I go to the next slide, you'll get a better idea as to what happens as that water comes in. There's a mulch layer at the top. There is a soil-based media, and then there's a rock base on the bottom. The stormwater comes in. It infiltrates through this. It removes sediment, and it then goes out the outlet pipe with treated water. The system is not designed to infiltrate into the ground. Okay, it's only designed to treat. But as you can see, it treats by soil, and in this case, soil and vegetation. But the primary mechanism here is soil because it's not tested in laboratory vegetation. Why not? Because it takes a while for the vegetation to basically root structure to grow and all that. And it's been decided that if the soil can do it, it would only be enhanced with vegetation. Next slide. This is another hydrodynamic separator inlet pipe. You see a flow splitter. You have a oil floatable skimmer. You've got an outlet weir. And this is a hydrodynamic separator. Again, I want to point out to you that the inlet and outlet pipes are aligned 180 degrees separated. You also have a manhole cover above, which allows you to access and to use with a vacuum vector type system to remove sediment that's been collected in the sump chamber. Next slide. To give you an idea how this device works, the water comes in from the left-hand, stormwater comes in the left-hand side. It hits this diverter plate. It goes both left and right, causes vortices, both clockwise and counterclockwise, because it can't get past the skimmer state. And that they then go all the way down, creating a detention time for sediment particles to settle out by sedimentation at the bottom, come up the other side, and then go out either through there's holes in the plate on the outside to the outside. So that would be another example. If you go to any of our reports, you will see the actual pictures. To some degree, some are better than others, I will be honest, of how the device actually works. Let me go to the next slide. Okay, and maybe before I do this, because this is a critical slide, were there any questions about the program, how the program is operated?
Yeah, there are a couple questions here, Dick.
Okay, all right, let's see what we have here.
So first question is, does the NJCAT evaluate or plan to evaluate for nutrient removal?
Okay, the answer to that question, as far as the NJBDP NJCAT program, no, because the department has not yet developed a test protocol for nutrient removal. Okay, but There's one that's just went up on our website that was a laboratory test of what was called a 3-cell unit. The third cell was a polishing cell that also removed metals. I have one in the works that'll be a field one, but they will not be certified by New Jersey. The certification for other removals such as phosphorus and metals is being carried on by a parallel program in Washington State by Washington Ecology, and they do all their on field testing. All right, and they do certify for removal. Do I think that we will go there? The answer is probably yes. But remember, and this is not, I'm not ducking the issue. I can only verify and DEP certify along with your regulations, and there's no test protocol right now. Another question here?
Yeah, one more. Can you speak in terms of the 80% TSS removal rate? How accurate is that?
Well, in the laboratory, it's very accurate. Well, and because we test with a given particle size. By the way, there are two things in the filter protocol. One is the removal rate, and B is the loading capacity. We ask them to test up to the point where the cumulative loading removal efficiency drops down below 80%. And then that basically says that is the maximum amount of sediment you can collect on your filter. And that is then translated into a drainage area. There's an equation that you have in your protocol that says, okay, if you can collect so many pounds in a year before you drop below 80%, that becomes your acceptable drainage. It's a pretty conservative number because it assumes, in a lot of these cases, it assumes that you're getting as much as, I think, 600 pounds coming off your site, pounds per year of sediment. So again, as best you can do it, yes. Where the issue is with filters and why many of the states are leery about filters is that if you don't maintain them, eventually they're going to clog. Okay, and we know that, and that's why we determine a maximum number loading. But it is A, in the laboratory, and B, it is with a surrogate sediment, which is basically a very, very tight sand, silt clay, a larger particle, less than 75 micron coming in, but it is a surrogate number. All right.
And then we have one more that came up. Does the debris captured need to be vacuumed out?
The answer is yes. When you get two things, there are two types of debris. You've got floatable, and you've also got sediment. The state requires that maintenance be conducted when you get to the 50% sediment section, loading section. So, for example, if your design is for a 12-inch sediment, in there, all tests are run, by the way, with a false floor with a 6%, with 6-inch false floor for removal. The reason being behind that is we feel that by that point you need to be cleaned out. So you're going to get better removal if there's no sediment because you got more detention time in there. Second of all, when you do your scour test, you have to have sediment up to that six-inch level in this particular example and show that it doesn't scour out. So to the extent that you maintenance, and this is the big bugaboo of all of these devices, these tests are all designed that they must be maintained at a certain point, and the test results show you'll get your 80% removal, as well as you'll get your 50% removal in hydrodynamic devices.
And one more kind of on the same lines, but maybe a little more specific. Can the debris captured in the BioClean cyclone cause clogging that will lead to flooding?
You mean backing up the system? Well, it shouldn't because and I will caveat that with another comment later on. But remember, this is all in the sump, okay? So it's not backing up the piping in the system, and the testing is conservative enough so that it's only we test with a false floor at 60%, 50% of the sediment storage capacity, at which point maintenance should take place. Now, obviously, if they never get maintained, then obviously everything goes down the tubes. Okay, it doesn't. Now, the only other possibility of backing it up, and I'll talk about that in a minute, is if sediment is being deposited in the inlet pipe, and then you go through a long time drought period, and maybe that sediment, caulks up and it cuts down the diameter of your inlet pipe. That is possible, and the new protocol is designed to handle that. I don't know of any cases that I've heard of, but you would know more than I do, that flooding and backup is occurring in the field. Obviously, if you have a major oil spill, because they do have oil retention usually above that, you want to get in there and get that out right away. And if you've got trash in that floating on the top, obviously they all build in a capacity, so you cannot that will not go out. But I guess if you collected enough of it and you got a really large storm, some of that trash could in fact get washed out. These are good questions.
And that's it for now.
Okay, great. I love it. I love the interaction. All right. Now this is the big message that I really want to leave with you. You say, why'd you waste all that time? Because I want to bring you up to speed. There's a tremendous misuse of the certifications by the manufacturers. I have found out that this is an incredibly competitive field. There's a lot of money to be made. I don't know the details, and sometimes the salesmen will come in, and frankly, sometimes the engineering firms are not as knowledgeable as they should be. So you will see plans coming in where they will have an MTD in it, and they will say words like NJCAT verified and NJDEP certified. Okay, and so this is my warning to you. Okay. First of all, not all NJCAT verified stormwater technologies are NJDEP certified. And you say, well, how could that happen? They didn't like what you did? No, it's not that. There are some states that feel that the particle size sediment that is in the NJDEP protocol is too stringent. It has a certain percentage of particles that get down to less than 5 microns. And certainly you're not going to remove that out of a hydrodynamic device, or probably not of a filtration device either. They want to see what can these units do with a different sediment PSD. In other words, different than the NJDEP sediment. And what that means is a larger D50. And D50 is the particle size diameter, which 50% of the mass is below that, and 50% of the mass is above it. In the New Jersey DEP protocol, the D50 must be less than 75 microns. Okay, a lot of other people want to come in and test with a D50 of 110. Well, obviously, that means you can get higher performance. One of two things: you can either get you can with a larger particle size get 80% removal with a hydrodynamic separator. But I always tell people it's easy if you're sending boulders in. They're not going to remain in suspension very long. Okay, so therefore, again, I just alert you: all certified MTDs have been tested with the NJDEP 7. That is probably the biggest area they'll try to get by you with. I want you to also recognize there are only 25% of the stormwater technologies to date that we verified are certified as are GI certified. That number is increasing. It will continue to increase. And there is on that website that I listed before, the NJDEP website, and I know that was up on the chat before. those technologies. Maybe if we go back a little bit, yeah, if you go back a little bit, you'll see the 7 ones that are in fact GI. They have been GI certified, and you can see that up there. And on that same website, you'll also be able to click on and find the our website, which will give you the verified reports leading to that. Okay. The next point is, and there's another one, I'll talk to the next one later on, and it says only the HSD configure that was tested has been certified. Now they will offer other configurations claiming certification. Remember, I tried to point out to you in those other diagrams, all units pretty much tested HDS devices have one pipe coming in and the other pipe going out at 180 degrees apart. So all the ones certified so far, inlet outlet configuration that is 100, they will come in and they will bring inlet outlet pipes sometimes which are not 180 degrees apart. I've seen them even come in at 90 degrees and then go out at the other side. In other words, if you look at a manhole, one would come in at 12 o'clock and the other would go out at 3 o'clock. Now, all the ones that have been tested come in at 9 o'clock and go out at 3 o'clock. Okay. The other thing they try to get by you with is multiple inlet pipes. Okay. They say they bring 2 pipes in and only 1 pipe out. The problem with that is you're now changing the hydrodynamics that go on inside the device, and therefore the performance that was tested, and verified for us, I can't tell you it's going to be there or not. All right. We're trying to allow, as we go to our new formula, to come up with ways of allowing them to do it, because certain devices are more amenable to these changes than others. Some actually will not work if you do anything else. And then the new thing I'm seeing a lot of are grade inlets, whereas, you know, it's drop down, comes run in, and the fluid comes directly drop down. Well, obviously that's a lot different than some of the ones you saw, which have some type of a rotational pattern, such as the Cyclone X we looked at. So you've got to be careful of that and leading the plans. And what's happening is the manufacturers are policing themselves very much. They raise to me and say, hey, you know, X is offering this in New Jersey, and then I have to go to Gabe. He's not happy. And then Gabe has to write a letter either to the engineer who approved it or the manufacturer and say, hey, you're misrepresenting your product. It has not been certified in New Jersey. So please be aware of this. I hate to make you policemen and policewomen, but this is just the nature of the business. Next slide. And I think you already know this. An MTD cannot be used in series with another MTD or media filter to achieve an enhanced removal rate. So, for example, you cannot put 2 hydrodynamic MTDs together, and which would, in fact, give you 80% removal because they're both at 50%. You get 50 of the first, and you get 50 of the next 50 gets you 30%. 30-25, you can get close to 80%, but you're dealing with entirely different particle size distributions into that second MTD, and you can't do that. And the same would be if it was a sand filter. Okay. Are there any questions on the misuse of certifications? I mean,
this appear to be.
This may be the most important part of it, so you don't get it. Okay. So Mike has asked the question. So I just issued a letter. Let's see, similar to NJ. Can NJ? I cannot issue a certification letter, nor will I. I only verify performance. That is and that's what makes this program so have national and frankly international recognition, because it's a combination of the two. And by the way, I haven't, because I didn't know what your time was. It's a fairly rigorous process, because after I get through with a report, verification, I go through all the data, all the stuff in the test laboratories. I then have to publish it for public review. And I can tell you that the other industry manufacturers go through that report with a fine-tooth comb. And there have been 2 cases in particular that which I was a little embarrassed about because I probably should not have let it got that far, but maybe 2 out of 40, I don't know. Still not good enough. That they didn't pass the review process. And if they don't, it goes to a third-party review panel. It's almost like the Supreme Court, who they don't know who it is, from a group that they have pre-selected. They don't know who I selected. I have 20 people, mostly academics, that then review the 2 positions and see whether it is. And the only way they can lose is if they haven't adhered to the test protocol. Okay, we have another question here. Jared Thompson. No, that's that. Obviously, if you have one in MTD that is certified at 80%, you don't need anything else. Now, when you go to structural BMPs like infiltration basins, that's not an MTD, and now you've moved out of my area of expertise. You've moved to your department, and maybe someone in the department can answer that question. All right, someone wants me to wrap this up. I apologize. Can you give me one more slide, and I'll do it in less than a minute. Okay, I want you to know I've said already that all technologies will be sunset that are HDSs, 7 of them by next June. And if they want to be recertified, they'll have to retesting with the new protocol. We hope to have a new filtration protocol in 2021, and it will not change much from the current one. So I don't think it'll require retesting. I could be wrong. And some of you may have heard about a new initiative called the STEP Initiative, the Role of Stormwater Testing and Evaluating Products and Practices. It's an attempt to go to a national program. Right now, the nation is relying on our program and Washington State. There's some feeling that a national program is going to help. This initiative has been underway since 2013. I may be in glory by the time this whatever comes, but you may hear about it, and I'm not going to spend any time talking about it. I thank you for your time. I apologize putting you up against the end, but if there are any other questions that come in, Lisa or Chengai, just get back to me and we'll answer them. Okay. Thank you for your time, and I appreciate the opportunity.
Thank you, Dick. We really appreciate your being here. That being said, I think that we are going to address the clarifications from the questions that could not be answered today at the start of Module 3 on Tuesday. I'm going to put up hold on one second. I have to take something off my screen. And can you see the quiz cover page?
Yep, it's up there.
Okay.
I can, but I'm not going to take it.
Okay. All right. So we're going to combine the break with the quiz. So I would suggest that you take the quiz first and then take your break. And because I know that we're going to be a little bit past 4 today. So with that being said, we're going to do the same thing as yesterday, except this time when you get to the web page, hold on one second, you are going to, I'm opening the quiz, go to quizzes as before. You're going to go to quiz 2. And if someone would paste the quiz link into the chat, I would appreciate it. The quizzes should now be open, given a moment to go through the buffer, and you may commence taking the quiz. All right, it should look like this, and here's the link at the bottom of this slide for the While you're taking the quiz, I will take an attendance report. And the time is 3:52. Would like to get underway by 4, but that's not even 10 minutes. So do your best, and thank you very much for taking the quiz. And we'll be back at 4 o'clock. And we'll see how many are not answered by then. Okay, for the people who still can't access the quiz, we will find a way to get one to you separately. I understand that some people have other activities and need to leave. And that is understandable. We'll go over the answers to the question. Your mark is here for the module. And if you want to discuss, any part of the quiz, just let me know. I have about 2/3 of the classes having finished it. So I think we're going to give the quiz another minute or so before we get to the review portion of the class. But if you have to go, I understand. Thanks, Jeremy, for letting me know. I'll still be able to see the chat, so I'll make note of that. But you can use your name on the quiz, but that makes sense. Gotcha. Thank you.
Okay, Lisa, are we ready to begin the review?
I think so. Let me see how many responses we have. Just one sec. We are about 98% completion, so I think it's okay to go ahead. If everyone else just finish up as best you can, and we'll get this underway.
Okay, so let's start the review, beginning with question 4. True or false? There is no longer a minimum or default value that can be used for time of concentration when using the Nrcs methodology. The answer is, of course, true. So there is, no longer a minimum TC value when using the Nrcs methodology. This is something that Lisa covered. Going forward, the assumed minimum value of 6 minutes previously published in Chapter 5 of the BMP manual must now be replaced by a calculated value. And what's the percent correct on this, Lisa?
92.
Okay, that's good.
Yep.
Moving forward with question 5, according to the NJ Stormwater BMP manual, what is the maximum roughness coefficient that can be used for sheet flow and calculations? The answer is A, 0.4. So this is also something that Lisa covered. In New Jersey, the maximum Manning's roughness coefficient that can be used for sheet flow calculations is 0.4, and that value is only for wooded conditions. So there is a 0.8 value in the National Engineering Handbook associated with woods with dense underbrush, but the maximum value allowable in NJ is 0.4.
We got 73% of that.
Okay. Question 6. What is the maximum sheet flow length for the pre-construction condition, assuming there is no physical constraint present to prevent sheet flow from occurring? The answer is B, 100 feet. So the maximum sheet flow length, which can be assumed for the pre-construction condition, is 100 feet, unless there's something physically preventing sheet flow from occurring within that 100 feet, such as a swell curb or inlet, in which case the actual distance should be used. Also, just to note that in the post-construction condition, the sheet flow length must be calculated using the McEwen-Spice limitation, and that was covered in the Stormwater Calculations presentation. What's the percent correct on this, Lisa?
92.
Oh, good. Okay, question 7. According to the New Jersey Stormwater BMP manual, what is the maximum drainage area which the rational method can be applied? And the answer is B, 20 acres. So as stated in the BMP manual, the rational method should not be applied to drainage areas that are greater than 20 acres. What's the percent on this?
Oh, sorry, 84.
Okay, that's good.
Yeah.
These are all good.
We still have someone with his hand raised. I assume it was for taking the quiz, but I didn't know if there was another issue at hand. Mr. Sabatini, is everything okay? I guess he left the chat. Okay. I guess he was letting us know he left. Sorry for the interruption. Where are we? Question 8?
Question 8, yep. True or false, a weighted average of the curve numbers for pervious and impervious areas can be used to accurately calculate the hydrograph using the Nrcs method. And the answer to this is, of course, false. Just to note, this is an error that we actually see pretty often in our audits. That leads to improper sizing of the BMPs used on site. So NJAC 7:8-5.7A4 requires runoff rates and/or volumes of pervious and impervious surfaces to be calculated separately, and using a weighted average CN will greatly underestimate the total flow rate and volume of runoff. What's the percent correct on this?
88.
Good. All good. All right. Question 9. So when determining the curve numbers for site design, the design engineer should assume that the condition of the existing cover is a good condition. When determining the curve numbers for the existing conditions, the design engineer must always assume that vegetated areas are in good condition. This is also stated in the Stormwater Manager Rule at 7:8-5.7A2. And what's the percent correct on this?
I am sorry to say the answer is 60%.
Wow.
60. Yeah, we were split. 20% said best professional judgment, 11% said fair, and 9% said poor.
Yeah, so actually the rule does require the use of a good condition for vegetated areas in existing conditions. So hopefully everybody knows that now. Moving on to question 10. True or false, the Delmarva Unit Hydrograph should be used in all areas of the coastal plain with no limitation? And the answer is false. So I guess what's critical here in this question is the with no limitation part of the question. The Delmarva must be used when modeling watersheds within the coastal plain region, since they are typically characterized by flat topography with average watershed slopes less than or equal to 5%, low relief, and significant surface storage in swales and depressions. That's unless, though, the design engineer proves that those conditions are in no way present on site. Then in that case, you can make the argument to use the SCS Unit Hydrograph. But in most cases, the overwhelming majority of cases, the Delmarva will be used in the coastal plain, but it's not completely without limitation, because there are those rare cases when the Delmarva wouldn't be appropriate. For instance, we don't allow the use of Delmarva Unit Hydrograph when sizing MTDs. And then also note that if the Delmarva is used in the precondition, it must also be used in the postcondition, and likewise for the SCS. What's the percentage on this?
81%.
Okay, that's good. All right, question 11. True or false? If the Nrcs methodology for calculation of stormwater runoff is used, type 3 rainfall distribution must be used for development in New Jersey. And the answer to this is false, of course. This was also covered in the stormwater overview presentation back on Tuesday, and Lisa covered it again today. The required use of NOAA C and D distributions in the NJ supersedes the use of type 3 distribution. So what's the percentage on this?
62.
Oh,
Yeah.
that was C and D. Yeah. All right. Moving on. Question 12. True or false? Pretreatment must be incorporated into the design of a small-scale GI BMP that has a drainage area greater than 1 acre, infiltrates runoff into the subsoil, and uses exfiltration in the routing calculations. The answer to this is A, true. So all small-scale GI BMPs, which are designed to infiltrate into the subsoil and have a contributory drainage area greater than 1 acre, must include pretreatment of stormwater runoff when using exfiltration in the routing calculations. So each small-scale GI BMP has updated chapters in the BMP manual, and you can find the pretreatment requirement details associated with those BMPs in their respective chapter. What's the percentage on this?
Oh, sorry, 87.
87. Oh, good.
Huh.
Okay, question 13. True or false? When the groundwater mounting reaches the bottom of a BMP designed to infiltrate, the infiltration into the subsoil will be adversely impacted. And the answer to this, of course, is true. The groundwater mound reduces the hydraulic gradient under an infiltration BMP, which results in reduced infiltration rate. What's the percentage on this?
95.
Good. Yeah, expected to be high. Everybody's listening. Question 14. Soil testing logs prepared in accordance with Chapter 12 are required for which of the following BMPs? The answer is E, all of the above. So, right, infiltration basins, detention basins, and grass swales all require a minimum separation from the seasonal high water table, and therefore, in order to make that determination, soil testing in accordance with Chapter 12 of the BMP manual is required. We may not have covered grass swales that extensively, but there is a required minimum separation from the seasonal high water table for them, and because if there's like frequent inundation or inundation for extensive periods of time, that will kill off the grass, which is the pollutant removing mechanism for that BMP. So soil testing is required for all three of these BMPs. What's the percentage on this?
46.
Okay, yeah.
Yeah.
Yeah, all three of those do need soil testing.
Great.
And that's because of the required separation from the seasonal high. All right, moving on to question 15. So true or false, the tested soil permeability rate must be used when calculating the drain time from an infiltration basin. And the answer to this is false. The design engineer should always use the design permeability rate when determining infiltration basin drain time. And the design permeability rate is just the tested perm rate with the factor of safety of 2 applied. And what's the percentage on this, Lisa?
20.
20%. Yeah.
Oh.
I guess you have to read carefully. The question states the tested soil permeability, when in actuality it's the design permeability. So it's just like it's misread maybe, hopefully. Moving on. Question 16, true or false? Direct observation to determine the depth of the seasonal high water table must always occur between January and April. The answer to that is true. So direct observation of the water table is only allowed between the months of January and April, and outside those months, soil modeling can be used to determine the seasonal high. What's the percentage on this?
72.
Okay, that's good. Question 17. When is it necessary for the design engineer to assess the hydraulic impact on the groundwater table? And the answer is B, whenever an infiltration BMP is proposed. So anytime a BMP that is designed to infiltrate into the subsoil is proposed, the design engineer must assess the hydraulic impact on the groundwater table. The citation from the rule that requires this is 7:8-5.2H, and we also have available on our BMP manual webpage the Hantosh spreadsheet, which you can use to assist in determining the impact on the groundwater table. But there will be plenty more of that in the next module on Tuesday. We have an entire presentation dedicated to groundwater mounting. What's the percentage on this?
81.
81, good. Question 18. How many soil profile pits and/or soil borings must be performed for 5 small-scale bioretention basins and 1 mapping unit that is each 450 square feet and scattered around the development? The answer to this is C, 1 soil profile pit for the soil mapping unit and 1 soil boring for each small-scale bioretention basin. Chengi covered this today. This requirement is detailed in Chapter 12 of the BMP manual. So for sites with multiple infiltration BMPs, each with infiltration areas equal to or less than 500 square feet, a minimum of 1 soil profile pit per soil mapping unit where the BMPs will be located is required, and then 1 soil boring per BMP. And if there are infiltration BMPs located in different soil mapping units, then each soil mapping unit must have at least 1 soil profile pit. What's the
63%.
Okay.
20% selected 1 soil profile pit for each small scale bioretention basin.
Yep. Check Chapter 12. It's pretty detailed, but it's all laid out there. Question 19. True or false? In a small scale infiltration basin, the 2-foot separation from seasonal high water table should be measured from the surface of the sand layer. The answer is false. Of course, a BMP separation from the seasonal high should always be measured from the lowest excavated elevation of the BMP. So in a small scale infiltration basin with a 6-inch sand layer, it should be measured from the bottom of that sand layer. What's the percentage correct on this, Lisa?
65.
Yeah, we always measure from the bottom of the sand layer. Okay, question 20. Where on the soil horizon should soil permeability tests be performed? And the answer is A, the most restrictive layer below the basin bottom and above the water table. So as noted in Chapter 12 of the BMP manual, soil permeability testing should be conducted within the most hydraulically restrictive layer below the basin bottom and above the water table. What's the percentage on this?
64. The next largest group of answers was selected B.
B, yeah. So B is, I guess we can almost work on, we can work on rephrasing this maybe for the next session if it's a little confusing. But B is like the lower bound on for where you should check for the most hydraulically restrictive layer. But that's not the point at which we should check. It's just the lower bound. So I don't know if Chengi wants to elaborate on that, but anyway, I guess that closes us out for Module 2.
Yeah, the next one will be on Tuesday, May 4th. And if you have additional questions, you're always welcome to send them in. Meanwhile, we'll work on the outstanding unanswered questions and have an update for you. And I want to thank you very much. Again, if something comes up in your schedule, you can email here or you can email me to let us know. Otherwise, we hope to see you Tuesday. Thanks very much for attending.